Good evening, everybody. Thanks for coming. I'm Paul Parkansky. I'm the chair of the West Michigan section. Want to thank you all for coming. Encourage you to look out for future events that we're going to be holding, especially a big special event we're going to be doing during Art Prize, so keep an eye out for that. But without further ado, I'm proud to have the honor to introduce Kathy Helmetag, a dear friend of mine, who is new business scout for Henkel Corporation in Madison Heights. She is a respected and well-experienced tribologist, as well as a motorcycle and Volkswagen enthusiast, quite a cook, one of the most interesting people I've ever had the pleasure to know. She'll be talking today about tribology, the intersection of chemistry and mechanics. I'll step out of the way and let her get going. Thank you.
Thank you, Paul. Hopefully everybody can hear me, and I hope I don't get too loud. But yeah, so my name's Catherine Helmetag. I'm what's called a tribologist, and today I'm going to talk about a very young science, a science that got off the ground only a couple of hundred years ago, and today is changing so fast that even those of us active in the field sometimes have trouble keeping up. I'm going to start with a little bit of science and history of the field of tribology, move on to some mechanical and chemical constraints, talk about something called viscosity, which is a material property of a lot of molecules, talk about a model that allows you to marry the chemical and the physical properties into one unique way of looking at a frictive contact. And then I'm going to talk about a real-world model. And the real-world model is really neat because it's really, really big, it's really industrial, and if you ever get a chance to see it in real life, I highly recommend you go. So what's tribology? People always ask me, is that like tribbles, like it's Star Trek? No, it's not. Tribology comes from the Greek root tribos, which means rubbing, and we just got our name back in 1966 for our science. Some Australians were visiting the UK. They were visiting a gentleman named Professor Dr. Alistair Cameron at the University of Leeds, and they came up with this idea that we should name friction and wear science, because before that it was just a bunch of chemists and a bunch of mechanical engineers that didn't really talk to each other. So they kind of invented the science right there in 1966. It covers not only friction and wear, but also lubrication, which is where chemistry most often comes into play as part of it. And it's only in the last maybe 20 or 30 years that people have heavily started to study the chemistry that occurs in the contact. That's where the lubricant scientists come in. So what my background is actually organometallic chemistry. So when I did my master's degree, you couldn't even get a PhD in tribology. In fact, you couldn't get a PhD in really anything that had anything to do with tribology, and I'm a little bit older than I look. So it's just recently we started looking at this stuff, but it's very exciting as an organometallic chemist because a lot of it focuses on how organic ligands bind to metal surfaces and metal oxide surfaces. And without that background, I wouldn't be able to do this. Back in 1699, which is of course an anagram of 1966, it looks familiar, a gentleman named Amundsen came up with the idea of friction. He looked at some of the things, some of Leonardo da Vinci's experiments, and he figured out that, well, now this was Amundsen and this was 1699, and this was actually the case up until about 5 years ago, that friction was basically independent of area. Now, friction is the resistive force to pulling. You've got a force, you've got a contact, say a block against a plane. So if you took your keyboard here and put it on a table and you're trying to push it across, the frictive force is the force that resists the movement. And it's dependent on the normal force, the force that's pressing down, typically. We just learned 5 years ago that Amundsen's law is actually wrong. Yeah. So we just learned a whole lot. And when I talk about the chemical mechanical model today, I'm going to talk about some of the reasons that Amundsen's law actually is wrong. And part of this research led to proving Amundsen was a lie. So when we do our sliding tests, in the case of the beverage can industry, I don't know, has anybody ever been to a beverage can plant, or you know what beer cans look like, right? They make millions and millions of them per minute in a beverage can plant. So those cans have to move on this big moving web, and they have to move extremely freely. They have to slide against each other. So one of the things you do when you make beverage can lubricants, that you're trying to lubricate all this machinery, is you actually test the resistance of the cans to moving against each other. And this is where this is basically the same type of test that Da Vinci was doing when he pulled his little blocks across the surface, and that Amundsen was doing when he decided that friction force was independent of area. So what happened next? Well, Coulomb happened. So you guys all know Coulomb's law, right? Everybody's heard of Coulomb? We know about the number of electrons in a mole, that sort of thing. So Coulomb decided that there was a difference between kinetic and static friction. And static friction is the friction of things that don't move. So it's that resistance to the initial motion. Kinetic friction is the friction during motion. So there's two different things we have to care about. In the lubrication world, we really care a lot more about kinetic friction. The chemistry side of things, we care a lot more about kinetic friction than static friction. Static friction is a little bit boring. This is what we call our third law. Kinetic friction, is nearly independent of sliding speed. So what happens here? Well, what could be happening between these two things from a chemical perspective? We ask ourselves, is there some sort of molecular adhesion that occurs between these little asperities, these little bumps on the surface? Why is kinetic friction different than static friction was our big question. We got into things like surface roughness back then. Before we started introducing chemistry in the contact, people strictly considered the behavior of the surfaces. So what were the material properties of the surfaces? What was possibly the chemistry of the surfaces? And this is why it was largely, tribology as a rule, was largely the domain of mechanical engineering, because it was a surface. And chemists didn't start doing anything with surfaces until we met Langmuir. Then we got into some more guys who looked even closer at those surfaces. This guy named Dennis Archard, and Dennis Archard said, well, clearly things stick together. And when two surfaces come into contact with each other and there's friction, it's because they stuck together and one's tearing the other one off. Well, that's a little aggressive, isn't it? Rabinowitz decided to talk about surface free energy. Now, Langmuir, of course, is our surface free energy guy, and I'm sure you've all seen a copy of Adams and Wilkinson somewhere. Anyway, he added surface-free energy to the adhesion wear theory and decided, well, if it's capable of sticking together, the friction will be higher. And if it's not capable of sticking together, so if the surface-free energy, if that delta gamma is too big, they're not going to stick together. Nam Su, who actually is a retired friend of mine from MIT, he came up with the idea of delamination wear, and he said, well, you know, it's nice if you stick things together and tear them apart, and it's nice if the surface energy works, but what happens when bricks fall? And what happens when your rod bearings fail and just big chunks of it come out? Well, he said maybe the surface energy inside of the material can result in a grain boundary failure, and the material simply separates because it's under too much force. But we're still not into chemistry yet, are we? We're still in the domain of mechanical engineering. So where does the lubricant come in? These guys, they were mechanical engineers. Love them dearly, especially Dr. Su, but I mean, mechanical engineering. They looked at everything, but we know that functional industrial systems never survive under wear conditions. Okay? Anytime you have a big industrial process, which is what I do for a living, is giant industrial processes, you need a lubricant. The most common place that everybody knows about lubrication is oil in their car engine. We think about lubricating a pan when we fry eggs. We think about lubricating a lot of things. Even soap on our skin is a type of lubrication. So we bring lubrication, we bring chemistry into these frictive contacts all the time. I mean, some people are even familiar with your tires hydroplaning on ice, maybe? That was a big topic this winter. So now we start to introduce chemistry into, we're up to the 1970s, maybe 1980s about with Nam Su, where we start thinking about what does the lubricant actually do. This is when chemistry starts to enter the picture. And this is why I want to stress, I love my science because it's such a young science. And the field is completely wide open for future research, especially on the chemistry side. The mechanical side, not so much. But on the chemistry side, all kinds of cool stuff. In the beginning, before anybody realized that chemistry was important, a gentleman named Osborne Reynolds started the field of fluid dynamics. If you haven't taken a course in fluid dynamics, if you haven't explored the idea of chemical engineering, This is one of the most novel, most heavily math-dependent areas of engineering world. In fact, I always like to say one of my cousins got his PhD for solving the Reynolds equation around 4 bends by hand. And this was 3 years of math. It's craziness, actually. But what Reynolds did was he came up with the concept of a hydrodynamic wedge. Now, to have hydrodynamics, it implies you have a fluid, right? What is a fluid? Fluid is typically some sort of chemistry. Thank goodness we now have jobs. So Reynolds looked at the representation of the behavior of fluids in confined spaces. Well, any journal bearing is clearly a confined space. We talk about a journal bearing, we've got 2 outside halves, and then we've got a shaft going around at high speed on the inside, just like crankshaft in a car, any motor, any type of bearing, they're all the same. So Reynolds came up with an idea that this was a very turbulent situation. There was a lot of motion in here, and the fluid was not sitting still. And it probably wasn't always flowing perfectly smoothly. But in his case, he said, well, I'm just going to use paraffin oil because that's about as Newtonian as it gets, and it's pretty chemically inert. And I'm going to try to keep this on the mechanical engineering side because I'm a mechanical engineer. Well, it worked up to a point. What we found was that speed and viscosity, we introduced this term of viscosity. This is the material property of resistance to flow. If you've had some polymer science, you know that as polymer chains entangle, they become stiffer and stiffer, and eventually you get to a solid. Lewis F. Richardson is a famous poet, and he said big whirls, big disturbances, have little whirls that feed on their velocity. Little whirls have lesser whirls, and so on to viscosity. So I love that. That's a lot of fun. But anyway, speed and viscosity govern the film thickness. Now, the film thickness is how much space is separating the journal in the center, the shaft that's rotating, from the bearing wall. Imagine if they were touching, and Archard and Rabinowitz and Sue were active, and they were tearing each other apart. That would not be good. That would be a big industrial failure. There would be wear. So Osborne Reynolds said, well, look, if this thing moves fast enough, that fluid is going to develop some sort of thickening behavior, and he called it the hydrodynamic wedge. And this is a representation of the pressure that builds up in the bearing. And you can see that as the speed increases, the position of the shaft changes inside of the bearing structure. Why? Well, gravity's trying to pull it down naturally. But that hydrodynamic wedge is pushing back. And that is how that works is very dependent on the fluid chemistry. If it is a pure Newtonian fluid, and if it is not reacting or interacting with itself, if it does not hydrogen bond to itself, if it does not pi bond to itself or anything else, it will behave like a pure Newtonian fluid. And you will get exactly what Reynolds predicted. Now, that's not always good enough, but we'll start there. So what Reynolds did was part of this is he created this lovely equation, and I know as a chemist I personally used to freak out whenever I saw a big differential like this, a big ugly one. What I did was I said, well, it's a circle. That means we can take one whole dimension out of it, and let's just care about x and y. So when I do this work, I only work in 2 dimensions. If you can't reduce it to 2 dimensions from 3, that's too much stress, honestly. So what he did was he decided, if we go back and we look at the previous slide, and we said speed and viscosity, he decided that speed and viscosity played a big role here, and that H, the separation of the bearing from the journal from the bearing, could be accurately predicted, given a perfectly Newtonian, non-chemically active fluid, could be very accurately and easily predicted. Yeah, and it actually works. We've had some work in the area of wire drawing, which is a beautiful, beautiful mechanical representation of tribology, because you can not only collapse it down to a plane, you can actually collapse it down, or you can not only collapse it to a circle, but you can collapse it to a slice. It becomes a very neat, very, very mathematically condensed equation. We've actually shown that in an industrial process, you can predict the minimum viscosity required to keep separation. This is why Honda now has engines with 0 weight engine oil,
because it's actually all that's required to run. And the beauty of it is viscosity, the resistance to flow. The lower viscosity, the lower the resistance to flow. That means less energy is being lost to friction. You get more power out of your motor, basically. Paul mentioned I'm a car freak. I'm a total car freak. And I can apply this every day, all those things that I'm interested in what I do with motors. There's math behind all of it, and it's neat, and it depends on chemistry. So when we look at this, we're actually Reynolds number here. This is actually the most interesting part of the equation. We have our height, which is our film thickness over here, and we've got viscosity. But Reynolds number actually predicts how much flow turbulence you're going to experience. And the flow turbulence is where we get pressure. Reynolds' equation was very interesting, and it became extremely interesting to two guys named Bowden and Tabor. I mentioned Alistair Cameron earlier. Alistair Cameron was busy at work proving all of Reynolds' work for these journal bearings and all this film thickness studies. Well, these two guys, Bowden and Tabor, over at Oxford, decided, yeah, that's good, but we have non-Newtonian fluids. And we know that fat works as a lubricant. So why does it work? Why does a solid paste work as a lubricant like butter or lard or coconut fat? Why do these things that are not Newtonian and are not particularly special, or they collapse in viscosity very rapidly? If you're familiar with Crisco or butter, when you melt it, the viscosity goes down dramatically with a little bit of temperature, yet these things function extremely well as lubricants. And Bowden and Tabor said, no, there's something going on. There's something more to this lubrication thing than just hydrodynamic wedges. And they started to ask a question about what happens as H, the separation of the journal from the bearing, in Reynolds' equation starts to get to 0. And they proposed something that they called the boundary condition. And the boundary condition is where the magic of chemistry in tribology starts. The boundary condition is when we say H approaches 0. In hydrodynamic condition, we have many, many layers of molecules. I mean, there's a lot of molecular layers in there. This is thick fluid flow. We usually say a minimum of 4 to 8 molecular layers in these contexts. In the boundary condition, though, and those molecular layers, they're oriented in the direction of flow, we learned. We learned that from Langmuir. In the boundary condition, though, something else happens. In the boundary condition, they don't orient in the direction of flow. They start to stand up. And now, the way the contact interacts with itself, the two sides interact, becomes completely different. Because as you can imagine, a polymer chain is long and thin. So 4 of them, 8 of them does not stack up to very much. But you take one of those, take oleic acid and put it up on its end, that's 18 carbons long. That's a lot of space, especially when it's standing up and it's tight packed. It's a self-assembled monolayer on the surface. It's very tightly packed. It's a very stiff layer. It's completely different than a normal Newtonian fluid. Without the attraction of the carboxylic acid to the metal or metal oxide surface, it can't stand up like that. And this is what got Bowden and Tabor jumping up and down. But they got that far. What they weren't able to figure out, though, was what happened when the two surfaces came into contact. Was there any chemistry going on there? And it was up until probably, well, I don't know, maybe 15 years ago was when people started to think about what happened as the contact closed. Before that, we all just assumed that Archard, Rabinowitz, and Sue all applied. Those physical, mechanical behaviors, adhesion wear, delamination wear, that's what happened when those two surfaces came into intimate contact. So what if Bowden and Tabor forgot a part of chemistry? What really is the boundary layer? So Reynolds put, the word boundary actually is, it's very basic. It comes from a boundary condition. Reynolds put the boundary condition of 0 to infinity. It's hard to imagine infinity in a lubricated contact. That would imply there is absolutely no normal force, so that wouldn't work. But 0 is extremely important. And in 1922, W.B. Hardy actually said, well, you know Hardy, he did stuff with electronics. He said, well, I'm going to look at this and I'm going to see if I can pass an electrical current through this contact. Since it's usually two metal surfaces we're trying to lubricate, he said, well, if they touch, then I've got contact. If they don't touch, then the lubricant film is still there. Now, Hardy, of course, is very, very curious about this, and he finds at this point that sometimes he gets contact when he doesn't think he should be getting contact. So he gets an electrical signal crossing the two surfaces, crossing the gap, when he doesn't think he should be. And sometimes he doesn't. And it was all dependent on what type of fluid was in the gap. This is one of the studies that Bowden and Tabor really had a lot of questions about, because they said, well, wait a minute, half his results don't make any sense. They got published anyway, but peer review wasn't what it is now. So at Reynolds time 0 was not really that small. At Reynolds time 0 was still microns, so you couldn't really get things in intimate contact the way we do today. There were no reliable sources of monoplanar graphite back then, or monoplanar mica. Approaching 0 back then was this very thick film, a minimum of a couple of molecular layers. That's all you could squish out over an area. Remember, Amundsen still applies at this time, so we have areas of frictive content. So we have to consider how close can we actually get those two together. It wasn't until maybe 1995 that we could actually get real planar contacts that were completely touching. So we really are going to define our 0 for Reynolds purposes as the two surfaces coming into contact. Now, I know everybody says, well, we haven't really talked about any chemistry yet. Well, what happens if you have a reaction in between those two? And the surfaces don't come into contact because they're physically touching, but they come into contact because they reacted with some chemistry, and that's formed a mass that has fused the two. That's also possible. This actually justifies the adhesion theory of wear. We go back to the boundary where bulk physical properties, our viscosity that our polymer friends love so much, isn't so much important down at the boundary. It's actually the chemical properties of the material in the contact that are going to govern how the frictive surface, how the frictive interface behaves. Chemistry really, truly does take over. But what's the limit to the boundary? Is it a chemical limit or is it a physical limit? This is a good question for chemists, actually. Boundary functionality by Bowden and Tabor is defined by the way they interact with the surface. Typically, anionic materials, metals are generally positive. Metal oxides have some residual positive charge. So you get things like carboxylic acids, you get amides, you get esters, you get anything with a double bond on it, will interact with a metal surface and will actually fixture and in some way assemble itself on the surface. We have something in tribology that we call EP. And EP stands for extreme pressure. EP is a very challenging regime to work in, and that's where I chose to insert myself into the science of chemical tribology. I said, well, Bowden and Tabor couldn't figure it out, maybe I can. And at that point in time, 10 years ago, that was a big leap of faith for everyone in the tribology community, I have to say. Chlorine, sulfur, and phosphorus are what we consider to be the extreme pressure elements, because when you react them with iron, you form relatively soft materials that are non-wearing. So they're very wear resistant, but they flow, or they have much lower coefficients of friction, which is the ratio of the normal force to the pulling force. Much lower coefficients of friction. And because they don't wear, even if you have that direct contact that Hardy observed, because he got an electrical flow through the two surfaces across the gap, you don't have wear problems. So you don't experience this cosmic damage to the two surfaces. But these materials only work when there is extreme pressure. Is the mechanism the same, was the big question. And actually, no, of course not. Because carboxylic acids, when they react with a metal surface, they form a polar interaction. They form a polar bond. They don't actually, quote, react with the surface. I mean, they can. But what we decided, or what I looked at, was, is there a difference between materials that absorb to the surface and materials that covalently bond? And actually, you form covalent bonds. So if you're an inorganic chemist, you can start making salts, but you can also make salts that flow. It's a big difference to go from a very, very basic polar interaction that's very weak. It doesn't take a whole lot to rip those oleic acids or those fatty acids off the metal or metal oxide surface. But you really have trouble to undo iron sulfide. This is a challenge. This is a lot of energy if you want to take that apart. So what happens to get a covalent bond? Well, you need a lot of heat, and friction, thankfully, generates a lot of heat. I'm sure you've all heard people say, you know, check your brakes and make sure you didn't get them too hot when you're going down a hill. Don't ride your brakes going down the hill. Well, that's because friction generates a lot of heat, and if you cook your brake linings and you cook your brake rotor, they won't work anymore. Why? Because they've changed chemically. So you no longer have the same frictive interface, and it doesn't work. Thermal energy drives chemical interactions. We know that. We know that there are activation energy barriers. There was this incredibly challenging question in lubrication science for many, many years. We called it the chlorine gap. The chlorine gap was the fact that chlorine worked as an extreme pressure agent at an unbelievable temperature and pressure range. But phosphorus only worked at low temperatures and pressures, and sulfur only worked at really, really high temperatures and pressures. There was this gap in the middle that you could only fill with chlorine. Everybody said, why is that? Why doesn't everything just work? Well, it's never that easy. So we started to say, well, how do we get that kind of energy? We know we can get a lot of heat in, but maybe your system doesn't have a lot of heat, and it still works. And a research group in Poland caught the idea that perhaps that when our chart applied and you started to really hit those asperities, just about the time we discovered that you could get physical emission of electrons. And they said, well, is that possible in a frictive contact? And when you consider that on a metal surface, a metal oxide surface, you have nanometer level asperities in some cases. When those are hitting, those are very, very high pressure contacts. And it was very quickly realized that, oh yes, you can throw a lot of electrons from those surfaces. And how do you get a transition state? You add electrons, typically to organic molecules, and you get some sort of transition state where you've got extra electrons, or you've opened up a bond somewhere halfway, and it's very, very reactive. So we've now figured out that there is some mechanical way to drive chemical reactions on these surfaces. And everybody kind of knew this was going on, but nobody knew how to talk about it even. So we get to this EP concept. We call it extreme pressure, and I really prefer to call it extreme temperature. So as H, that distance between the two surfaces starts to go to zero, and you actually can generate some of these electrons, and you actually can generate these thermal gradients that you need to generate. How do we get there? Well, we close the gap because we've gotten there. When we build an EP film, when we start to run these reactions, we actually do close that gap. H does come to zero because now you're riding on absolute fully mated films. The surfaces, the actual base metal surface, may still have a shape to it, but it has formed a flowing film in between, and they are now actually completely in intimate contact because of this physical flowing layer between them. It's not a traditional lubricant layer like a Newtonian fluid. It's actually a reacted layer on the surface, which is really, really cool. So we start to go back to Reynolds, and we say when H is large, bulk properties take over. So all you have to know is material properties. Those are your basic paraffins. When eta is the bulk viscosity of the lubricant, and when H gets small, we ask what properties are important, are physical or chemical? Well, a lot of it's both. And what I did was I defined eta. Instead of saying it's just viscosity, I said it's the frictional contribution of the lubricant to the contact. So I said, well, I don't know if it's just viscosity. I know it's resistance to flow. So I took I took the old definition of viscosity, the resistance to flow, and used that instead of traditional Newtonian viscosity. And we were able to get somewhere. So what do we look at eta? When we look at eta, for extreme pressure, it's easy. It's basically the bearing surface is an EP film, so it's the shear strength of that metal salt we've generated on the surface. It's relatively easy. We did chemistry. It still has mechanical properties and material properties. We just have to apply them. But boundary is another story, and this is the area where the most research is being done. It's the most exciting area because, honestly, none of us really know what's going on yet. We know that for H equals infinity, that's hydrodynamic lubrication, we don't allow any interaction. I keep talking about these non-Newtonian fluids and isoparaffins that just don't do anything. And we know that friction force strictly comes from internal frictive flow. We know in the boundary only polar and adsorption reactions occur, and we define it as the boundary character of a lubricant based on its ability to absorb. So if it can't absorb, it doesn't have any boundary. It doesn't have any boundary capacity. And you know what's funny is that this lubrication business, you used to call somebody back in the 50s, you would call up some guy called a lubrication engineer and ask him to fix your problem. And the guy would kind of wave his magic wand and hope. We're just now in the early 2000s, coming now into the 2010s and so forth, we're just now starting to understand how this works. So if you were ever interested in industrial chemistry, here you go, this is the field. So we stop at H equals 0, and we start to look at these EP properties. Well, frictive force comes from the yield strength of a new compound. And we joke up here about, ooh, that was deep. Well, in 2003, when we first presented this, I got chased out of the room by 100 chemists and tribologists and mechanical engineers and said, that can't be. Today it is. Today we know this is actually true. So it was really exciting to do some foundation work, but it's also difficult because I know now what I don't know. And what I don't know is really, I know the boundary layers stand up and I know they do a lot of things, but I don't really know how they work. So why bother? It's very simple. We have good mechanical engineers to support us as chemists, and they know exactly what their contacts look like. But it becomes a job of a lubricant formulator to figure out how to get the right chemistry into those contacts for the right operating conditions. And we take things away from art and move them into science because art does not, in fact, actually pay particularly well. Science pays. So what I want to do is go quickly through a real-world example. And the real-world example is going to be steel rolling. Everything around us, we find steel. It's typically sheet steel that's been formed into a shape. The pans for the chairs here may or may not be steel. They may be plastic. The legs of the table are assuredly steel. Your unit body of your car or your box frame of your truck is most assuredly steel. To get steel, we start with iron ore. We cook it down in a Bessemer furnace. We make raw steel out of it. Those ingots have to be remelted and poured out and cast. It's then rolled down. The problem is, again, oh, it's lubricants. It's a black art. And no one knew how to predict which lubricants were going to work or not in a mill. Now imagine a steel rolling mill. You can imagine how big your car is and how big a piece of steel you need to make the side of a car. Well, this is what a rolling mill looks like. It's that blue thing in the back. That's as big as a football field when it's a 6-stand mill. The strip going through it is upwards of 12 feet wide. It is a lot of steel. It starts out this thick and is squished down to millimeters, submillimeters, through many, many processes. Now imagine if your job is to figure out how to keep that mill moving and not have big wads of steel pile up in between the rolls. Well, you better be a pretty good tribologist, huh? You better be a pretty good friction and wear engineer. This is what it looks like when you have a hot strip mill. In this case, it's a little bit narrower strip, but you can see it just keeps going. In this case, the steel is yellow, so it's about 2,000, I think around 2,000 F. It's very, very hot. It's a very challenging chemical condition, you can imagine. Remember we said we needed heat to drive chemical reactions? Well, there's your heat. We don't need a whole lot of friction here. In fact, in the rolling contact, we don't really want a whole lot of friction at all. We have something we call the neutral point, which is where the strip is moving at the same speed as the working roll. The working roll is the thing that's applying the pressure and squishing the steel down. We have what we call the backward slip zone, where the steel is moving slower than the roll, and the forward slip zone, where the steel is moving faster than the roll. Try to come up with a more challenging contact mechanically. I dare you. This is about as bad as it gets. this is a bit of a challenge, and it's a couple thousand degrees, just so you don't forget. Lubricant is flooded onto the strip. We're trying to keep the rolls from getting too hot, because if the rolls get too hot, they're going to bend, and then the steel will get out of tolerance, and it'll get bowed and buckled and wavy and messy. It's actually really kind of interesting to watch a steel mill fail, because literally the steel just balls up in between the rolls and starts spitting out everywhere. It spits out the top, and the first time you see it, it's very frightening. It's very loud when it fails. You don't want to be there. After that, when you sense that it might be being bad, you can see all the operators in the mill start running away, because no one wants to be there for that. So we apply a lubricant to keep it cool. We're trying to keep the work roll separated from the steel. We don't want them to touch, because then our chard would apply and we'd start sticking, and then really things would go bad. You can even get it where it wraps around the work roll. Yeah, you pretty much just recycle the work roll after that. It's just gone. So the lubricant does all of that, and it does something else which is kind of interesting. It provides post-process properties. You've got so much heat in there and so much energy that you can actually treat the steel surface just by rolling it. So you can produce a completely different chemical surface on the steel just by going through this operation. It is really cool. So we call this a slide contact. It's very similar to tires on the road. It's very high speed. It's extremely high load, because let's face it, you don't squish steel with your fingers. And the reduction, so the percentage reduction, this is how much reduction we take in the strip. This is what governs how much we can squish it, because it can only go so fast out of the back end and only so fast out of the front end. I mean, if you squish it too much, eventually it actually starts to back up, and you get these little kind of bumps in the steel as it goes, and the thickness varies very dramatically over the surface. So we know there's a lot of surface chemistry, and we know that there's enough heat in there that there's probably something going on. We also know it's moving fast enough that no matter how much surface chemistry you have, it's moving so fast it's a Newtonian fluid anyway. You get to a speed point where you build up hydrodynamic wedges. I mean, you actually have to. So then we look at the slide roll ratio. This is a little bit of math, which is a way of defining how far out on the work roll we can go. Like how many degrees of the work roll can we go before the steel will actually back out of the roll? It's just important to know that that exists. So what we did was we had a customer who said, well, you know, we have this little toy mill, and we're going to test a bunch of lubes, because they tried running a bunch of tests, and none of them really correlated. So they sent us this data, and they said, well, here's some oils we ran, and here's what we were able to achieve for roll speed and roll force. Now, the roll force is very important, because that's the amount of pressure you're putting down, and eventually you can overcome the mechanical strength of the mill. So you really don't want to go there, because then your mill stands break, and that's expensive. Your work rolls fracture. Those are really expensive. So you want to be able to get out to these very, very high reduction ratios. 50% is basically we've reduced the strip thickness in half in one pass, so through one pair of rolls. We want to be able to do that at very high speeds and very low roll force. This roll force is very critical. That's what we're shooting for. We're shooting for that big reduction and that big roll force. Well, you can imagine that if we go back a little bit, we probably produce an area contact here, right? Ammonton and the pulling with the blocks in the area. The tests they were trying to use did things like, well, we took a line contact, because it's a block, so it's a square rectangle thing on a ring, so that makes a line contact. We're going to test friction there. Do you think that has any relation to a steel rolling mill? No. Then we took 4 balls and stacked them up and spun the top one. We got 4 point contacts. No relation to a steel rolling mill. We don't have any sliding. We have sliding, but we don't have any slip. We don't have that forward and backward flow motion going on in these contacts. They looked at something called a pin and V tester, did the same thing, and then they came up with this thing from Japan, and nobody really knows what it does, but it doesn't work either. So we found a device that was developed actually by our friend from England, Dr. Cameron, called the elastohydrodynamic lubrication tester. And it's a point contact, which is not like our steel rolling mill. But what's very interesting about it is you can vary the speed of the steel ball and vary the speed of the flat plate that it's rotating against. And by doing that, we can introduce sliding into the contact. So we can't really create a rolling mill because that would be very expensive in the laboratory. But we can actually control the amount of slide and rolling that's occurring in the contact with this thing. What we did was we looked at something called traction versus slide roll ratio and a Strybeck curve, and those are fancy tribology terms that you don't need to know about, or don't need to know very much about, but you do need to know that when we put a Newtonian fluid in there, it produces these beautiful stacked up curves. It says, oh, hydrodynamic lubrication, it says. Perfect, pure hydrodynamic lubrication. And as the viscosity goes up, the traction or the friction coefficient goes up, because what is viscosity? It is the resistance to fluid flow. That is the frictional contribution of the material in the contact. It works. But when you start to get into things that are not white oil, which has an R squared of 995, and you start to put in things with boundary activity, well, fatty acids work pretty good, but even chlorinated paraffins worked okay, but phosphate ester? No. Oleic acid? No. Sulfur materials? Not really. So something is active chemically with these materials that causes you to deviate from normal viscous behavior. And we kind of knew that, but we couldn't really tell until we started matching chemistry to mechanical conditions. You had to have both. In this field of science, you have to have both. So if anybody ever makes fun of a mechanical engineering degree, remember, it's not a bad thing. What's interesting was when we started to look at the phosphate esters in the oil, now those had a very poor correlation coefficient, of course. When we put them in a pure white oil, there was not a whole lot of deviation, and they behaved very hydrodynamically. But when we put them in water, this is called hysteresis. Hysteresis means going in one direction is very different than going in the other direction. And if you look at the amount, the traction coefficient, it goes up. What happens when it goes up? There's more friction. And when there is more friction, there is more heat. And when you get above a certain point, it starts to come back down. Why? Because you have gone over the activation energy barrier. Wow. If you ever questioned activation energy, right there. We saw all kinds of wacky stuff. When we started introducing changing temperature, we could get the curves to do all sorts of things. We started to actually pull together the idea, even when you ran forwards and then backwards versus backwards and then forwards, we could do different things. And we were able to start actually creating a model for how boundary materials, how these materials that simply behave by very weak polar or electronic absorptions start to act on the surface of a purely mechanical contact. And we were able to start developing what we call the chemical-mechanical model for lubrication. We ran all kinds of this stuff. It was a lot of fun. And then we started even going on to optical micrography. If you look, you can actually see where we ran. You can see that there's changes in the surface. Well, these are for various materials, and the more active, the more polar or even covalently active they are, the more things change, to the point that we got this. When you throw that surface into the SEM, you get holes in it. And those holes were extremely high in phosphorus, in inorganic phosphorus, no less. Even in the most lightest weight boundary lubrication condition, we had succeeded in pulling the phosphorus off the phosphate ester. We decomposed the phosphate ester in the frictive contact. And that is why a lot of phosphorus in your engine oil is bad for your catalytic converter, because it will come off. So we did some other stuff. And what we found in the end was we went back to our rolling oils, and we did those same kind of tests on the rolling oils. And when we first did the correlation, it didn't look too good. So we split it out, and we said, well, what if the base oils are part of it? So the things that have paraffinic base oils, which are over here, so these more less chemically active base oils, versus those that were esters, which are relatively chemically active, and all of a sudden those correlations improved dramatically. Now, from all this work, what we were able to do was study a very large rolling mill in an industrial application and make a predictive judgment about what lubricant would work best. And we nailed our target reduction, we nailed our target roll force, and our target speed on the first try. And that was the first time that had ever been done in a steel rolling mill. So it sounds like, oh, she's just talking about all this stuff. But the truth is, predictive testing and understanding how chemistry works in a mechanical contact is a huge key part of making everything work today. So it's a backwards science. People say, oh, lubrication stuff, it's all, nobody cares, it's not important. It's very, very important, because when we do it right the first time, no one notices. And that's a darn good thing. We kept going, we didn't find very much. But what we did find was that our traction versus slide roll, so this one specific test we were playing with, really tracks well within groups of base oil. So as long as we minded our chemistry, very, very closely minded our chemistry, we could do extremely well with predicting the behavior in the mill. We found this other test, well, it might tell us if the steel was actually going to go in. What's really dangerous and what's really bad is when you try to put the steel in the mill and you have a rejection. Because you've got your hot continuous caster pouring steel down that line, and you really want it to feed in. Otherwise, you have lots of 8-inch thick folded up hot steel coming at you at a couple, I don't know, probably about 20 feet a minute. That's not pretty. On the chemical side, we found that all these materials had sulfur in them. We never reacted them, but boy, we sure did react phosphorus. So we actually showed, yes, the chlorine gap is real. We were able to corroborate all of the results we have from all the other testers where we specifically test sulfur, phosphorus, and chlorine. So we found that this chlorine gap thing is truly real. We didn't actually test any chlorine in here because we didn't want to damage the tester. We were very concerned about damaging the actual tester, so we didn't put any chlorinated materials in it. But we also found, that this particular tester is unique because it does this Reynolds type stuff with viscosity and Newtonian fluids and hydrodynamics, but it also can reach the boundary conditions that we have so much trouble studying and understanding. We found a whole lot of anomalies. We found that we could actually define, if you gave me a curve or gave one of our tribologists at Henkel a curve, they could actually say, yeah, that has this particular material in it and it was run in this manner. It was so incredibly predictable. And we found that not only does certain types of chemistry have these predictive curves, but they can override other types of chemistry. So we can get very specific about which regime we're active in. And sometimes you can get a little bit of blurring. So when we looked at those correlations, we could see that sometimes things didn't line up that well. But the chemical effects in tribometric outputs turned out to be a relatively simple project, but it was very, very dependent on having the right equipment. And understanding how chemistry played a role in these contacts was extremely critical to interpreting the data. So without an understanding of chemistry, no one in the tribology community would have been able to interpret this. We absolutely needed chemistry to figure out how to make this work. So we say, know thy tester, preferably prior to use. So thank you very much. I'm happy to entertain any questions. Yeah.
Corrosive properties of the lubricant must have a pretty important role. Do you take that into consideration?
Absolutely. So the question was regarding passenger car motor oil and corrosion properties. Corrosion properties are very, very critical. We typically say we start corroding when we enter the boundary regime because without some sort of interaction with the surface, you're not going to transition into that next regime. And of course, without serious changing of the surface, you're not going to enter the AP regime. The trick is managing it. So we want to balance oxidation or changing to the surface with the mechanical properties of the surface, and we also want to make sure that any oxidation or changes we do to the surface are positive for the lubrication condition. Anti-wear additives are very typical of this. This would be your zinc dialkyl dithiophosphate. And the idea behind them is to produce, so to corrode this, literally corrode the surface. You're oxidizing your phosphate, you're phosphatizing the surface, creating a zinc deposit.
but you want it to be controlled, and you want to make sure that it's more wear resistant than the base metal that you're coating. Yes?
May dovetail partially at least with this question, but do you look at, and if so, what have you learned about examining the off-gas right at the point of compression between the rollers, and can you engineer that to give a protective gaseous barrier, or is there a cursor? But there's a zillion questions off of that.
Yeah, absolutely. In lower pressure contacts, we occasionally see that sort of behavior where there will be formation of a gas layer, but it's typically very rare because when you're looking at an industrial lubricated contact, it's typically relatively high pressure. If you were going to look for a gas layer to form, you would actually start with a gas. So you would work with something like an air bearing. So we try to avoid. We do try to avoid gas formation, and it's a very sensitive discussion because typically we're not worried about generating a gaseous barrier. We're worried about the release of materials into the environment. So any sort of outgassing would be very, very negative in a typical situation simply due to environmental release.
Wasn't quite my question. I was looking at
The strip?
the thin strip, yeah, when you have that magma, for lack of a better word, and it's so hot, obviously there is off
Oh,
gas.
yeah. So there's like basically boiling.
And then how can that be engineered to
Yes.
benefit the process?
Yes, and it actually is. What you see is it blows. So if we go back to the model of the, let me go back to the model of the mill here. What you would typically see is you'll have a lot of evolution of gas on this side, but by the time you're a couple of degrees into the contact, you're well past the compression point of steam. So you will have, again, a full liquid in the interface all the way out to a few degrees before you exit the contact, and then again you will start to form a gaseous layer. And the advantage of that is it actually blows the strip off the work roll. So we are looking, especially in cases where we're using a water-based lubricant, in these type of situations, we are absolutely looking for that. And it's typically steam. We don't want the other molecules to gas. We want just steam gassing here. So.
You mentioned a zero W instead of 5W oil. Is that useful for automobiles or things like that, or what would it be used for?
Well, right now, as part of both the U.S. and the EU's mandates to higher fuel efficiency, one of the biggest gains you can have in a modern internal combustion engine is reduction of internal friction, so engine component friction reduction. And to go back to our Newtonian model, any friction in the contact is going to consume power. So as we reduce viscosity, we reduce the internal friction in the contact. And you start to see engines that are designed to run at those tolerances and designed to run with those types of oils. So where a ratty old BMW Boxer motorcycle won't run anything less than 20 weight because the gap between the rod and the main bearing is a mile wide, in a relatively modern gasoline motor, you'll see very, very, very small gaps in the particular journal and shaft combinations, and those are designed to run on these very, very low viscosity motor oils. But it's a combination of chemistry and mechanics coming together to enable that. It is not simply the oil. Putting zero weight oil in my 14-year-old Volkswagen would be basically a recipe for fusing the crank to the block. You know, it simply does not, it cannot generate enough pressure in that. It cannot generate a hydrodynamic wedge because there's simply not enough friction to get all those molecules balled up together to form that wedge. So you have to run a heavier weight. So it's very much tandem designed to work together.
That kind of leads to my question. Could you just speak about the synthetic lubricants that they put in motorcycles and cars. I've got friends who are, well, I'm a motorcyclist. Too,
Oh, let me talk all about group base oils. So we start with group 1. Group 1 is your paraffinic base oils. Okay, these are straight chains. They have very limited branching. We go to group 2. Group 2 are what are called the naphthenic base oils. These have sometimes ring structures. They may have double bonds. They're very, very heavily branched. These two particular groups are your old dyno oils. These are pure distillates out of a refinery. There is no reaction going on. Then there may be a little bit of whitening possibly, but there is no cracking. There's no recombining of anything. We're going to leave group 3 alone for a little bit. We're going to head straight to group 4, which is polyalpha olefins. These are combined from ethylene, so they are actually remanufactured oils. You take your distillate, you crack it down to ethylene, and you reassemble it into PAO. And group 5 is esters, so carboxylates. Now group 3 is a long story. Group 3 is what happens when you take a naphthenic oil and you start to do what we call make an intended reacted product out of it. It is a marketing term. So the group 3s are they're accepted as synthetics thanks to a lawsuit filed before the United States Supreme Court, but they are much closer to their cousins directly out of the refinery. They're what we call very lightly cracked oils or lightly hydrotreated oils. They are processed. If you put up an IR, it's relatively challenging to separate a group 3 base stock from a group 2 base stock. You have to know a fair amount about its manufacturing process to sort it out. Now again, your component design is very, very dependent or is going to predicate your oil choice in a vehicle. So your seals, for example, are going to be specific to a group 1, group 2, or a group 3, group 4 blend, or a group 3, group 4, group 5 blend. And that has to do with how the polymers absorb the oil and whether they swell or not. It's a war that drives me crazy. I'd much rather argue additive packages than argue base stocks, because today's base stocks are so good. They're so well made. I'll even forgive a group 3. They're extremely well made, and it really gets down to the additive packages that are used to supplement the base stocks. So that's really where.
So I've got friends who say, oh yeah, I had the synthetic oil on my bike and I forgot to refill it and I drove the thing for 1,000 miles with no oil in it.
Well, again, that's going to be the additive package. Remember, if you go back to the boundary layer versus the hydrodynamic operation, the ability of the additive package to react with the surface and generate an anti-wear film is what's going to govern how long you run it for. The likelihood of actually running a bike engine for 1,000 miles with no oil in it, I don't care what was in it beforehand, that did not happen. Let me be clear, I've been doing this for 20 years, that did not happen. Basically not going to happen. Did he drive it to the grocery store and back? As long as it was in the same zip code, I would buy that. I will not buy anybody going 1,000 miles on a motor with no oil in it. It's just not. Yeah, motor oil, PCMO, or passenger car motor oil, is one of the most hotly debated hobby topics out there, and it's very entertaining. It's a kind of a minefield, and it's at the same time a lot of fun for those of us who work in the industry, because the amount of misinformation is very, very high. And there's a lot of stories being told. The truth is there's only 5 kinds of base stocks out there. There's only so many refineries producing those base stocks. Everybody's buying the same stuff. And there are only really 2 additive suppliers to the whole industry. So there's a very, very small range of stuff that's available. Do you like the blue bottle or do you like the red bottle kind of deal? That's what it a lot of times comes down to. And you do find even that some of your bargain basement, dollar store brands are actually basically identical to some of the stuff that's $25 a quart. So, because you're looking at chemically the same materials, and they are, by the model, going to function the same way. So it does work. So abide by your car's operating manual, your car's owner manual, and you will always be fine.
Anything else? Go ahead.
I wondered if you could elaborate a little bit more on what you were talking about, approaching the boundary condition, and you get two surfaces in intimate contact because you have a reactive layer that's present.
Yep. So
We were talking about chlorine, sulfur, and phosphate. Maybe this is my own ignorance, but it almost sounds like you have a monomolecular layer of an ionic liquid that's forming, or am I way off base?
you're not as far off as you think you are. We are, the tribology community is currently a little bit at odds right now about exactly whether we have an ionic liquid forming or what exactly is in there. We know it's a covalently reactive layer because when we take them apart, it's a whole different compound, and it is a physical layer on the surface, and it varies in thickness. So we know that it's a physical compound. Now, how it behaves, we know that it's shear strength dependent. So we know that the typical friction in an iron to iron surface, so let's say a steel to steel interface that's been lubricated with a chlorinated paraffin, we know that the coefficient of friction will be very similar to the flow resistance of iron chloride, molten iron chloride. But is it behaving as an ionic liquid? Is it simply behaving as a molten salt? We're not that far yet. So if you need PhD topics, I'm handing them out for free. So, does that help?
Yeah, thanks.
All right, I can speak to Kathy's expertise at the hobby side of the engines. She and I spent a race weekend once where we went through three engines.
I think three, yeah.
3 engines in a race car.
And
There's
ironic,
actually a piston still hanging on my garage
I
wall.
do. I have one on my desk.
So if there are no more questions, I don't want to keep anybody here too long. I want to take a minute to thank Kathy for a very interesting talk. I think we should all take a minute, thank her. Appreciate it. And I'm sure that Kathy will be around for a few minutes afterwards and be willing to answer any other questions you have.
Absolutely.
So, thanks everybody for coming out. Again, keep an eye on your emails. If you're ACS members anyway, keep an eye on your emails for a big event we've got planned for Art Prize. If you're not ACS members, join. See one of us that looks a lot older than the rest of you for information on how to join, and we'll get you hooked up. Thanks everybody for coming.